Okay, in the concluding lecture of week 1, I just introduced you to the general formulation of systems. So, as said, we will deal with finite dimensional systems or systems which are represented by ordinary differential equations. We will not deal with general formulation of infinite dimensional systems or hybrid systems. So, we will restrict ourselves to finite dimensional systems. So, we will be talking both with interested both in continuous and discrete time linear finite dimensional systems, and these systems usually arise from linearization of nonlinear system. So, we will sometime later in the course talk about methods of linearization and also limitations of linearization. We will talk about some different methods also of linearization, right. So, in general, so all systems are described by a set of nonlinear equations, right. So, you will have if I just were to write it in more general terms, you will have n state variables related via a nonlinear relation f between the states and the inputs. I will also be interested in measuring the outputs for obvious reasons, which are also some nonlinear functions of x and u. So, usually my notations will be I will have a system of n states, m inputs and p outputs together with some initial conditions which may be required for me to at some stage compute the solutions, or we will see how that goes a little later in the course. So, I can just write this down in a compact form as x dot equal to f x comma u, where f takes values from R n cross R m to give me again some values in R n. So, this will be a general notation that we will follow, right. So, R n would be an n dimensional vector space. We will learn those properties of vector space in the next lecture. R m will be an n dimensional vector space where my set of inputs come from. R n is where my set of states come from. In the example, for example, in the case of the inverted pendulum, my states were 2 dimensional, input was just R1, right. It was just a little perturbation or a torque that was applied. Okay. Similarly, with the outputs, right. So, outputs again it's like a map from Rn cross Rm, the state space, the input space to the output space. You could have p outputs, or we have not so far explicitly defined outputs, but for example, in the case of the pendulum I could measure, for example, the velocity as the output, the angular velocity, or even the position maybe, for example, as the output. Okay. So, let us do a little example of this one, right. So, let us say that I take a simplified model of a car, which is also called a unicycle, again from this famous book on nonlinear control systems. In this control I have two control signals. One is like the rotation, I will call this u2, right, and then one is just the translational motion, right. So, just u1 here. I can just go, so what I am allowed is movements which are like this and also movements which are like this, and that will define, so it will cover all the state space of my car, right. It can go anywhere in the R2 plane. Okay. So, the speed of the rolling, right, this is controlled by u1 and the rotation is controlled by u2, then I can write down the equations in the following way, right. So, the change in x1 direction x1 dot, the change in x2 is x2 dot, and then x3 dot. This is a simple relation which we can derive, right. Cos of x3 sin of x3 0 here, and then x3 dot is simply the directly proportional to u2, right. So, this is an example which looks like this, right, of a general form of a nonlinear system x dot equal to fx comma u. Special class of systems are which are affine in inputs, as we saw in the case of the nonlinear pendulum, right. So, again I will not derive that again. So, here instead of f being from Rn cross Rm to Rn, f is just simply a map from Rn to Rn. Similarly, G is also from Rn to Rn, right. Similarly, with the maps h and k, we can as an exercise you can just write down what the domain and the range of these maps are. Okay, so once we perform the process of linearization, I would be interested essentially in two kinds of systems, right. One is continuous time systems. I use the word here invariant. I will elaborate on this shortly. Continuous time systems, x dot t is axt plus but, y is cx plus du. So, in most cases when it is obvious, I will just write xt as just x. So, similarly, when it is obvious, I will just kind of omit this argument just to make the notations a bit compact. So, well, you can see that A is a n cross n matrix where the system is xx is in Rn, say U is in Rm. So, B will be an n cross n matrix. C will be, okay, if I have p inputs, then C will be a matrix which is p cross x dimension, and similarly with D. That's, and this will be same even if I am looking at a discrete time system. So, what is the time invariance in these cases? So, by time invariant we essentially mean that the system parameters A, B, C and D they do not really change with time. And so, they are just constant. For example, say a mass or a resistance or an inductance, say that they are just constant over time. So, I do not really have to worry about any change in the system parameters. Time varying systems where I know, well, maybe that, say, maybe my fitness level will change with respect to my age. So, I can say, well, that can be modeled as a time varying system where the parameters essentially are the ones which are varying with time. A, B, C and D are now also some functions of time. Still, these are still linear systems. Right? There is nothing that is adding to the complexity here. I am still looking at linear systems, but where the parameters are changing with time. For example, if I can write as f equal to mx double dot is a linear system, f equal to mtx double dot is also a linear system, just that it is time varying. Maybe the mass changes with time. For example, if I look at an automobile, the mass would change it with time because of the fuel which is being consumed. Now, this time varying can be generalized to something called linear parameter varying systems. We will not really explicitly deal with these systems. We will deal a bit with time varying systems, but it is interesting to know what are these parameter varying systems. So, if you buy any equipment, right, say you will say, well, its operating region is between, say, 10 degrees Celsius to 60 degrees Celsius. What happens outside the range? Well, it is not guaranteed to perform because some parameters might change. For example, I know that resistance can vary with temperature, or some other parameters of the system can also depend on pressure or humidity and things like that. So, whenever the specifications of the equipment are to work within a certain atmospheric conditions, could be temperature or pressure, it essentially means that outside those range the parameters might change, and therefore my performance of the system will also change. A little simple example would be, in most operating regions V would be a linear relation with R, and R would be fairly constant. But if I say R is different depending on temperature, then that is a parameter varying resistance. It is actually depending on the temperature. Let us revisit the predator prey model, right, of what parameter varying could actually mean in some of those cases. So, where we had that, okay, that A, B, C and D governed how the system actually behaved. So, A was the rate at which my small fish was increasing, or multiplying. Some obvious observation would tell us that one way of modeling this could be, or one way of influencing the rate of growth of the small fish could directly depend on the amount of food that is available, right. So, the rate of which S grows is a function of food supply. So, this I can just add an extra term or extra maybe flexibility to model this as a parameter varying system, and you could visualize many of this. I can maybe sometime during the course quote you some literature on parameter varying systems, even though that will not really be our aim to comprehensively look at those. So this ends module 1. So from module 2 we will start learning some basic tools from linear algebra, starting from vector spaces till some matrix algebra, which will form a bulk of tools that we will use in this courses through the rest of the course. So as I suggested, it would be nice for you to look at some comprehensive lectures on linear algebra. Even though we will teach you what all we need through the course, we will give you a set of problems to work out apart from the regular assignments. And I really hope that you spend a lot of time doing the module 2 and 3 in detail so as to have a smooth transition through the rest of the course. So see you in module 2. Thank you.